Okay, says we're live. So, hi everyone. Today we're just going to have a conversation between Vandy and Darryl. Um, I guess it's really all that needs to be said. If you guys want to get started, go ahead.
Okie dokie. How are you doing today, Daryl?
Good, and how are you?
I'm doing all right. I'm in like a bit of a funk today for some reason, but I've been looking forward to this all day because yeah, I don't know. So uh, you are well are recognized probably by our audience for having opinions in particular about like the Big Bang um, model and the cosmic microwave background, um, and interacting with those topics a lot in side chat, and that sort of I think the topics kind of that we most wanted to discuss today and to sort of flesh out to get a more I want to get a better understanding of what your position actually is. I don't want to straw man you or anything like that because I think that you do have asked good salient questions, and I think that there is a tendency that people think that you're a flat earther or things like that, and I think that that's not accurate at all. So yeah, do you want to respond to that? I guess not the flat Earth thing, but everything I just said, sort of.
That's all true. I do try to stir people up. Um, I'm like everyone else for most of my life. I've bought into the Big Bang theory, the Big Bang model, as plausible. But my career was, you know, in electronics and whatever engineering. Um, is to know how things work, so you can know how the world works like you do as a living. That's the idea. And um, the the model of the Big Bang, if you really dig into it, has a lot of problems, and it has to make a lot of assumptions. So what I would be interested in is a quick rundown of what you propose the model is,
Yeah.
um, how it works, and based on what science and physics you'd use to come up with that narrative.
Okay. Yeah. Great. Yeah, that's exactly where I was going to propose that we sort of start a discussion of exactly what the model is that we're talking about, so we don't talk past each other. So when I talk about the Big Bang model, what I'm referring to is the idea that the universe was previously in a that the universe as we see it today has expanded from a much denser, hotter initial state, and specifically that the data are entirely consistent with the universe transitioning from an opaque, ionized situation to a transparent, non absorbing sort of medium, and that as a consequence of that, all of the photons that were being emitted and scattered off of all of the various free charges then began streaming more or less unimpeded on average, certainly on average unimpeded through the cosmos, and now we see them today. And so what we're seeing in the cosmic microwave background is sort of a surface of last scattering. I am not including the entirety of the lambda cold dark matter model. I'm not including all of the details about dark matter and dark energy. I'm talking about the idea that the universe was initially in a hot, dense state, and that the decoupling of photons from electrons is responsible for the very uniform phenomena that we call the cosmic microwave background.
So that seems like, in general terms, and it feels like you're starting with a conclusion and trying to come up with the physics to explain that conclusion. Um, so, what evidence of of an observation or a principle in physics um, would you have applied to um, to come to the conclusion that there's a surface of large scattering of light and this hot condensation of the light elements um, coming from that process? What's the basis for that model?
Well, there. So the number one piece of observational evidence, I think, is the cosmic microwave background. However, it also the idea of an expansion of space-time is falls out very naturally from general relativity. So we have sort of a model of space-time that has been validated by every experimental test that we have sort of been able to specifically check. I mean, we've even measured things like frame dragging, for example. However, the number one piece, I think, would be the cosmic microwave background. So I think that they're simply it is very well explained, I think, by the Big Bang, and I can't think of anything else that plausibly explains it. If you come up with, if somebody comes up with an alternative model or hypothesis that does explain the data as well or better than the Big Bang, then I think you would find that a lot of physicists and people would change their mind about it. The specific aspects of the cosmic microwave background that make people think that it is a surface of last scattering is it is incredibly loud, for one. It is uniform. You see it everywhere. It doesn't vary over time. And it matches spectroscopically like a perfect black body. Those multiple things together make the explanation that it is radiation that we see from a black body very reasonable to me, just on its surface. I think that those observations, the uniformity in particular, how steady it is across time and across space whenever you look at various parts of the sky, no other model, dust clouds, including huge dust clouds, can match that. Along, well, those and I mean, it's all of them together. It's the uniformity, and it's also the black body factor. So, I think that is sometimes underappreciated because dust does not produce light like that. Stars do not produce light like that. Black bodies produce light like that. And
A black body is just matter radiating light, radio waves, light as a function of its temperature.
no, it's
So
not. That's not
a pink
accurate. A
a
black
pink
body
black
is
body
not.
radiator has a spectral output as a function of its temperature, isn't it?
A perfect one, yes, but
I mean,
a and but my point is that the emissivity of an object has to be 0 for it to radiate as a perfect black body. 0. It cannot reflect any light. It can't be transparent. A transparent object, a perfectly transparent object, will not radiate energy. It's certainly not as a function of its temperature. Maybe you could imagine. I don't think it can radiate energy at all, actually, because due to time reversal symmetry, if it's radiating energy, that means that it would also be able to absorb that energy in a time reverse process.
Well, a black body radiator doesn't imply that it's black. It's
It
just
does.
at a thermal equilibrium, and it emits as much energy as it receives.
Well,
The sun
that's
is not black, and it's a black body radiator.
it's not though. It's
It's
not a
not.
black body radiator.
Well,
It's not.
well.
It's not a perfect one.
There's the ultraviolet catastrophe, which was some of the starts of quantum mechanics, is that
Yes.
the sun doesn't completely fit the black body spectrum, but a black body.
That is not what the ultraviolet catastrophe is. The ultraviolet catastrophe is a prediction from classical electromagnetism that the spectrum of a black body, or the spectrum of radiation coming off of a source, should increase monotonically with frequency. Yeah, with frequency, because the naive calculation that you get from the energy associated with light and electromagnetic waves from a classical perspective, not from the quantization, the quantum mechanics perspective, where the energy of a photon is equal to Planck's constant times its frequency, that it was the deviation of that prediction at ultraviolet frequencies that was the ultraviolet catastrophe. I don't think it had much to do. The sun may have been the example that was often used, but I don't think that the sun was the main thing in the ultraviolet catastrophe. But I want to emphasize that the black body curve is an idealized case that emerges when an object absorbs every photon that is incident upon it, which is what a black object is. And then it also emits those photons, but the reflectivity of the thing, maybe I might have gotten the emissivity thing. It might actually be that the emissivity has to be 1 for a black body. This is one of these cases where I forget ellipticity. I always forget if 0 is for a circle or if 1 is for a circle. It's that sort of thing. But an object which is not a perfect black body will deviate from a black body spectrum according to how much radiation incident upon it does not absorb. Dust, the sun, everything that we sort of make is a non-perfect black body, and it modifies the spectral output. And you can actually fit that if you're able to perform a measurement on an object and see what its absorption is as a function of wavelength, then you're going to be able to produce a emissivity corrected black body spectrum, which is distinct quantitatively and in precise ways from a black body spectrum.
I just wiki plots of the black body curve and its wavelength of light emitted versus temperature.
Yeah, if it is absorbing everything, a transparent object, a perfectly transparent object,
It's
with
just
some
absolute temperature. It's not what it's receiving or what its temperature is going to be in the future. It's just its temperature.
That's false. And to give you an argument as to why that has to be false, correct me if I'm wrong,
Perfectly
but
insulated enclosure which is in thermal equilibrium internally contains black-body radiation
yes,
and will emit it through a hole made of there. That's how you measure it.
yes. But my point is that two objects that are exactly the same temperature are not going to have the same thermal spectrum.
Yes, they are.
No, they aren't. That's simply not true.
Well, why do you say that? How?
Because the black body condition comes from the nature of how the equilibrium and how the statistics the statistical mechanics of the distribution of the energy that is in there will go according to the Boltzmann factor of the mode of energy. So when you do the calculation, and when if you have a box, a three-dimensional box, and you assume that it's all in thermal equilibrium, and you don't assume conservation of photon number, and but you do assume that all of them are being absorbed. You have to assume that. If you don't assume that, it doesn't work. If 99% of them are being absorbed, it's pretty close to a black body, but it will be different. A very reflective, like, silver ball at some temperature does not give you the same spectrum as a ball of graphite. It
That
just doesn't.
fully get what you mean, but the idea is that an object inside a perfectly
Oh,
insulated
yeah,
enclosure.
yeah,
So it's not receiving any light, it's just at a temperature. Right, you put a pinhole in the enclosure and it'll radiate light at the spectrum um, at the spectrum as a function of its temperature, and that's black body radiation. That's the formal definition of it.
the black body radiation has a very specific spectral content, and that spectral content requires the thermalization of the photons.
And why would this recombination event follow a black body radiator?
Excellent question. Excellent question. Because the 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 state of the universe at the time of recombination, and there are actually a few different sort of close by timescales. It depends on exactly when you define recombination, because the transition from a completely ionized, when basically 100% of the atoms in the universe were ionized, the transition from that state to a almost completely non-ionized state, what took a little bit of time, but it was actually pretty brief. And the transition, when all the photons sort of transition from being able to go, and they transitioned to being able to move unimpeded through length scales that are long enough that we see them today, was a very, very, very sort of brief slice of time cosmically, on the order of just a few thousand years, really. But that's not your question. I got sidetracked, sorry. Your question was, why would the universe in the ionized state be a perfect black body? Is that what your question sort of was?
Yeah, it's essentially what I'm implying is that this recombination period is where matter condensed out of from a very high energy state. Is that how you would
It's
describe it?
when it's when matter already existed. The protons and the
So
electrons,
there was
they already
protons and
existed.
neutrons and electrons around. So it was a
Yeah,
classic plasma.
yeah, exactly. And the it wasn't until actually the plasma fraction, the ionization fraction of the, well, I would say interstellar or intergalactic medium, but there were no stars or galaxies yet. It was all a very uniform hot plasma that transitioned to being a very uniform hot gas that was lightly ionized. And over a pretty brief period of time, the ionization fraction dropped low enough that the photons became decoupled from the electrons. So the photons
Do we have
and the
any
electrons were in
equivalent of
thermal
that
equilibrium.
sort of state of matter? Do we have any, like, a plasma science that
Oh yeah. Oh yeah.
would
Yeah.
describe a state where
Yeah.
photons have to decouple from electrons?
Yeah. So a gas of ionized protons and electrons is opaque. It just is, because I think it's basically because of Compton scattering. And a photon can scatter off an electron, and a photon can always
But you
scatter
can
off an
see through a
electron.
plasma, and you can see light
Not
coming from the plasma.
the if a well, how far?
Well, that applies to everything, doesn't it?
Yes, it does. It absolutely does. But
Is there a law? Is there a physical,
it,
a law in physics that it describes this, that all the light's contained within the plasma and it's not radiating any light, or um, you know, black body radiation, whatever you want to call it, and um, then when it condenses down, it then suddenly radiates light.
it was always radiating light. What happened was the mean free path of the light over a brief time period became basically infinitely long, because it stopped being absorbed by the electrons, or stopped being scattered by the electrons, and stopped being sort of mixed up. So these you sort of, you were asking one question, and then you also asked another one. So I want to stay just briefly on the idea that this is not a controversial, this is not a sort of strange fact that a sufficiently dense collection of ions will be opaque to electromagnetic radiation. That is, you can compute the mean free path as the ionization density decreases, either because the actual particle density decreases, or because the ionization fraction of the particles decreases, because now the electrons and the protons are hanging out together. Then your mean free path is going to get longer and longer and longer. But and it is certainly the case, for the record, that the interstellar medium is actually a lightly ionized medium today. Because, I mean, technically, if it's, well, okay, since it's lightly ionized, then you can still call it a gas. People get hung up on that. But the density is so low that the probability of a photon at these wavelengths propagating through the universe, actually being scattered by something, is really, really close to zero.
That's okay. We'll just accept that for the moment. You said that relativity implies the Big Bang.
Relativity and
Isn't relativity more like evolution is to abiogenesis?
a little
They're
bit.
not the same subject.
Yeah, a little bit. That's fair. What I was gonna say is the concept. So, what the Big Bang is in part is the idea that the universe, meaning literally like the space of the universe, began expanding. And expansion or contraction of space time itself is the natural result of the Einstein field equations. It turns out that you actually have to balance things really, really, really carefully in order to get a universe that isn't expanding or contracting. And it was why when Einstein was finishing up his sort of uh, proposing the theory of general relativity, he asked astronomers of the day if the universe was expanding or if it was contracting, and they said that, or if it was static, and they said that it was static because this was before Hubble, and certainly before like all of the more recent things, but besides Hubble, and he was like, oh, okay, well that's kind of a if it's static, my math doesn't really work unless I add this constant. So he added this constant called the cosmological constant, denoted by lambda, and that sort of made the theory kind of work. And then later they made observations that convinced people that the universe was expanding, and he
So in
revoked that.
essence, like the universe is going to relatively works regardless of whether there's an expanding universe or a non-expanding universe. And Einstein's original equations implied a static universe. Well, it actually didn't address the problem at all. As you said, they went to astronomers. And why would you ask that question? Why would there be a question of is the universe expanding?
Because he's trying to create a model that matches observations, so he should probably read up on what the observations are.
What? All right, that's good. That's great. What observations were there at that time?
It's not particularly great ones, since at this point in time, I'm not sure they were convinced galaxies existed. I don't actually remember when that was like
That's probably true. But
the
what observations implied an expanding universe?
when he asked the question. There really, I don't know that there were many. They certainly
There
were
were
convincing.
none.
People didn't think that the universe was expanding by and large. They didn't. Most people thought it was static.
Well, um, what would have prompted that question?
Why is the universe expanding? Is it
No,
static or is it?
why would anyone ask if the universe is expanding?
I don't understand the question. What do you mean? Like why? But
Yeah,
that's their job. They're scientists.
why would you make an assumption that everything we
I,
see outside the Earth is expanding? Why
yeah, I
isn't it
think he's
just
asking.
existing?
Yeah, like what was the impetus that prompted the question?
Well, for on whose behalf? Because
Like, was it redshift or like what was the observation? Something must have made them say, "Hey, we need to look into this more."
the initial one was Hubble's measurement of correlation of redshift with distance. That
Lemire
was the
proposed a
one
red.
that
Lemire proposed an expanding universe 2 years before Hubble's observations.
yeah, his motivation, I don't know. I was
The Jesuit Catholic priest.
yeah, yeah, I'm
So I
familiar.
think about that and I think, well, what real world evidence would he have? And you know what the Jesuit sect
Like he might have
is,
gotten lucky.
um, to prompt the question, um, well, essentially, to have a creation myth. Where would a Jesuit Catholic priest get that idea from?
I don't know. I haven't read much about him. For all I know, he got lucky. For all I know, he had a weird dream or something. Um, I,
Or maybe
I
you read it in a book somewhere.
uh, maybe, but it certainly
like
was not. It
Genesis.
was not the established. It was not the consensus that the universe was expanding at that time. That's it. It wasn't. the The consensus changed to that after observations like Hubble's and the follow up to Hubble's, and the thing that really kind of convinced everybody except for like Fred Hoyle was the CMB. But if you're
Not
asking about
redshift. Like
the
redshift is
that
the
the
fundamental
red
basis of expansion, isn't it? That's and the CMB is just some proposed mechanism that happened
well
along the way. So the initial. So what was the impetus of
well you can have expansion without the CMB.
before we measured redshift, before we discovered redshift, and of course, well before we discovered any CMB, you know, someone asked the question: is the universe expanding? And um,
Yeah.
like Charles Darwin wandered around and spotted fossils and finches and pondered on the available evidence, and then came up with a model that might explain how all this works and gave us evolution. What was that process for the Big Bang?
It was observation. So if you're asking about the people that came to that point of view before Hubble, I don't know, and I don't care all that much, because people have a diverse set of viewpoints. Um, People have all sorts of ideas about things. People are curious about things. People ask questions because they're curious about things. They know that, things exist now and things are behaving a certain way now. So how were they behaving earlier? What was the previous state of affairs that led to this state of affairs? I think it's a very natural question. What made particular individuals ask the question before there was compelling observational evidence? I mean, pick any reason. I don't know.
So even like theists, they start out with what they consider as observations and real world information to develop their worldview and world model. Um, Flat earthers do the same thing. The quality of the evidence is not great, but that's what they do. They look at the real world from their perspective, and in their minds construct a model and then try to justify that model with whatever
Yes.
observations and theories that they pick. How is that different than the Big Bang?
I mean, fundamentally, it's not. That's how all humans work all the time. Because
All right,
we don't
that's
have
fair
access to
enough.
other.
What if
Yeah.
the body of evidence starts to turn against you? What if when you do the flat Earth, you start seeing things that don't agree with your model, and people start telling you this doesn't make any sense? Um,
It-
uh, there's
Yeah.
there's two options. You can change your model. You can tweak the knobs, or you can say, well, maybe the model's wrong, and if the model's wrong, I can just throw it away. Those problems are no longer problems. They're actually an opportunity for finding out what the
Yeah.
truth is and how reality actually works.
I agree.
So what I'm saying is, was this scientific methodology for the Big Bang theories good science?
Given the fact that most physicists were not convinced that the Big Bang was an accurate model until the preponderance of the evidence was what convinced them. The more and more reliable and numerous observation of redshift, of the fact that things that are far away are moving far away, that is measuring the present day expansion of the universe, unless you can come up with a better model. for it. Now,
You don't need a better model to show that an existing model is wrong, although
we
it
don't.
helps.
For the
And I
record,
and of course I've got a better model, which is no Big
okay.
Bang, and that seems to solve a lot of the problems in Big Bang cosmology, the crises in cosmology as they call them now.
Yeah, there's totally a crisis in cosmology. For the record, there absolutely is. Cosmology has a lot of open questions. There's a lot of ways in which our present theories have issues. I'm not denying that, but that's like saying that you have to throw out Newtonian gravity because it doesn't match the precession of the perihelion of Mercury. Should they have di-
So you
completely
should.
thrown?
Newtonian
I,
gravity is perfectly valid for
I didn't.
like everyday use, but as a theory, it has been upended by relativity. So
Yes,
as a scientific principle, it is incorrect.
I think that that's far too blunt of a way of saying it. I
Well,
think that
that's um,
okay,
I
but
don't
then
want to.
you can never. I don't. In that situation, you can't call anything correct unless all possibility of error and alternative explanation has been ruled out, and that becomes a sort of semantic argument. If you want to say it's incorrect, okay, but all of
Yeah,
our theories are
but
incorrect.
what we're
Fine.
talking about here is the creation of the universe. So it's not like a little thing. It's either gonna be created or it's not.
The
There's
Big
like
Bang isn't
no
talking
in
about the creation
between.
of the universe. It's talking about an earlier state of the universe.
Well, yeah,
That's
like
different.
yeah. Um, essentially, you're saying if the redshift's expansion, if we wind back the clock, it's got to come to one point,
It doesn't. Well,
or not one point, but it's got to
come
essentially
from a
be
smaller.
smaller than it was
Yes.
at the present
Yes.
time. Right?
Yes.
So
But
that's pretty much all you have as the evidence for it.
no, that's all you have before. It's it's so you could have expanding. You could have the same correlation with distance and recessional velocity that is observed without, for example, having the Big Bang. It could be the case that the universe was never small enough for it to have been opaque. The thing that and I'm sorry to sort of be repetitive, that really convinced physicists, because this was not the universal point of view. It simply wasn't. And it's not the universal point of view now. I don't know if you did a poll of cosmologists today about whether they think the lambda CDM model is the best available model in the literature. I don't know if you would. I don't know what percentage you would get, but I don't think it would be above like 95%. I could be wrong. I don't know. I'm not a cosmologist. It's one of my deepest fears talking right now is because I'm talking not in my field. But the
Oh, I
the
think you were
cosmic
talking
microwave
as
background
a
was the piece of evidence that convinced people.
um, I think you're talking as a honest researcher. Um, but
As
you,
an honest researcher?
yeah.
Well, I
Um,
appreciate that. Thank you.
um, which is what science is supposed to do. You're supposed to just look at the facts and you know come up with you know an explanation for what you see. Is
Yep.
essentially what science is. Um,
Yep.
so, all
Do,
right,
would would you have so if you want to say that our cosmological models right now are wrong, fine. I'll concede that point. What I'm but they're not. I don't. I think it's highly improbable, and I think the burden of proof is on somebody else to provide a model of why do we see the cosmic microwave background if there was not a surface of last scattering when the universe was at some pretty hot temperature, and then the recombination epoch happened, and now we see all these photons go through. Why do we see this signal at this very precise spectrum, which cannot be reproduced by any known material between us and the surface of last scattering, and is uniform
yeah.
across the sky, and is so loud? The energy of the photons in the CMB, there's like,
Oh yeah,
it's
it's
a
a strong
lot.
signal. It's right. It's almost like you're sitting right next to the transmitter.
Yeah, except it doesn't have any of the variations and that you expect from being near the transmitter. It's the same everywhere in the sky, and
Well,
it
that's
doesn't
I
change
find
over
that that's
time.
a little bit contentious. I find that fitting the
Uh,
black body spectrum is not is not that's what black bodies do. That's the theory. Um,
yeah, black
being
bodies.
being a perfect black body or a normal black
It,
body is the same thing.
it no, it's not. No, that is categorically incorrect. An object which has a noticeable level of like transparency over that scale is it will not produce a black body spectrum. That's simply not true. A transparent object, a perfectly transparent object, and I am aware that no such perfectly transparent object exists, will not radiate any energy, no matter how hot it is. Because if it did, it would just
No,
keep on
a
radiating
transparent object will radiate energy um, as a
until when?
function of its temperature. A transparent object will radiate energy.
And okay, so how cold will so as it radiates energy, it will cool down, right? This transparent
As
object.
everything does, yeah. If
Yeah.
it's emitting more energy than it's receiving, it'll cool down.
Well, it's not receiving any energy. It's transparent. It's not receiving any energy. That's what
All
transparent
right.
means.
Well, then it's just a function of its temperature,
Okay, so it's emitting that energy, and its temperature goes down,
and
right?
it'll eventually go down to absolute zero if it's truly
Yeah,
not
yeah,
receiving any energy.
yeah. And that doesn't happen. That is a direct violation
That's because
of
no
the
matter
second
can
law
not
of
receive any energy.
it doesn't.
You
It's not
can't put
radiating
matter in a
energy.
state where it's transparent to all energy.
You're right. I understand that, but there is that it is still the case that the spectrum is going to be modified based on the absorption properties of the material. This is not a cosmological question. This is you can think of it from a thermodynamics point of view, because if it did, then you're going to have a violation of the second and I think also the third law of thermodynamics, and it also just doesn't make any sense from a microphysical perspective. The physics of how matter and radiation interact is it actually is kind of in my wheelhouse, and you can't have a
It is.
radiation sort of event without having a corresponding absorption event. An object that is the more transparent an object is, or the more reflective an object is, the more that its spectral properties, as a function of temperature, are going to deviate from the spectral properties of a black body. This is a very key point, because it saying, oh, all things radiate as a function of their temperature. Yes, all real objects in the universe that are made of baryonic matter, as far as I know, do radiate as a function of their temperature, but they do not radiate with the same spectrum because they have different emissivities.
Okay. All right. So the key point of data to confirm, like differentiating the black bang CMB radiation from foreground dust, with some clear evidence, is the holy grail of Big Bang cosmology, isn't it? Some key signature in the radiation, because what you see is pictures of the cosmic background radiation that you see that is from the Big Bang. It's certainly not what the raw data looks like and what signal
It is.
comes into the receiver.
To a
They
part
have
in 10,000 it is.
no.
Yes. I
So how do you justify that?
I but because when they Kobe, so the Kobe satellite measured the monopole. The Firos instrument on the Kobe satellite measured the monopole and the dipole signal of the cosmic microwave background, and it could not see any deviation from a black body at a part in 10,000. I read up a lot on this over the last week. I tried to find, and if I am wrong, please correct me, but I'm pretty sure even when you're looking right at like a galaxy, you still see that same pattern, because the foreground noise is actually only you have to the noise that's polluting this thing, that's polluting the raw data, is the signal to noise ratio of it is closer to 100,000 actually. It's extremely uniform. You have to look
Okay.
at deviations. You have to look at deviations at a very, 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 very small fractional amplitude in order to see them.
Okay.
So the raw signal really is a lot more uniform and kind of glaringly, powerfully black body.
So you can look at foreground dust, and
Yeah.
you can receive a signal in your receiver that you can tell straight away that thermal radiation is either from foreground dust, which is that happens to be at 2.7 K,
It's
or
okay.
um, or Big Bang radiation.
So there. So is your model that foreground dust, or that there's a uniform sort of density of dust at 2.7 Kelvin?
Yes, that's not a model. That's a fact.
Okay, that's not true. One,
That is
it
true.
wouldn't look like that. If you had dust at whatever density you desire, existing all throughout. One, why is it so uniform? It wouldn't be that uniform. Because it would
Thermal
be emitting
equilibrium.
to the gravity. It wouldn't be that uniform gravity.
It's in thermal
The
communications
call
with each other.
that doesn't mean that it's
It's
going to be of
particles of
uniform
dust
density.
bathed in 2.7 K radiation, and
Well,
so they're absorbing as much as they're emitting. So it's the same thing.
okay, dust absorbing as much as it's emitting will not radiate with a perfect black body. It won't. We've sort of discussed that particular aspect to death. So
But I don't know why. Anyway, yeah, sure.
I understand. I understand,
I'll,
but
I'll give you that. Yeah.
we don't need to keep on dwelling
Yeah.
on that. But I do maintain that. But if I'm wrong about that, it also would not be uniform in density, and the amplitude that we see from the CMB is so uniform that a cloud of
That's an
dust
excellent point, because
would It would be
The
clumpier, and
original
it's not.
the original models predicted the opposite to uniform. They predicted a lumpy CMB,
Yeah, yeah,
and
they actually did.
they had to add an extra layer of complexity on top of that and introduce inflation. Is that not correct?
Yes,
So
this is one of the best
now the
arguments against the
smoothness
CMB.
is a feature and not a bug.
Yeah, so what you're talking about here is the horizon problem, and that is, and you're correct that the solution to that, that's most popular currently, is inflation. And that it is true that it was surprising to see that the sky over there was the same temperature as the sky over there, because they, without something like inflation, should not have been causally like interacting. But
Not overall temperature distribution, but lumpy, like as we see our universe now. It's clumpy, it's lump, So there should be. It's not,
oh,
as you said, the horizon
oh,
problem is another problem, but the smoothness problem is that the CMB should be lumpy and it's not. And to smooth out those lumps, you introduce inflation, an inflationary period. So
oh,
think of an uninflated balloon. It's all lumpy and crinkly, and what we sort of see our universities as now. But to solve that, you inflate the balloon and smooth out all the all the wrinkles, and that's So originally the model was the CMB should be lumpy and bumpy, and um, all right, we'll add an extra layer, add another knob to twist, and we'll introduce inflation. What you're saying is that um, the communications between different regions of the universe to bring it to that um, smooth temperature is further than the speed of light.
yeah,
So it's beyond its, what's it called? Causal horizon.
yeah. And that is why inflation it was introduced, and the models that we have now do a very, very good job of explaining that at a quantitative level with not that many parameters. You're able to fit the power spectrum of the anisotropies that we see really like stunningly well, according to models which include all of the sort of pressure effects, the acoustic oscillations as the universe was cooling down in its early years, and they explain why the anisotropies are so low for inflationary models within a certain parameter range, because those sort of smoothed out the quantum fluctuations that would have been the impetus of them sort of fundamentally, and we still see the imprints of them now. However, and though all of those things are built on top of the kind of Big Bang, and so I think it's at least a stunning coincidence that the models match the data so well. They didn't have to. The models that are the most popular now are the most popular because they match the data. If
Yeah.
it sounds
Does it give you any pause to consider that your models predict exactly what you predicted,
no,
and what you
because
predicted supports what you measured? Does it feel like it's a bit revisionist?
no, because it's not. You have physicists come out and they predict 20 different models, then they collect data, and the data rules out 19 of them. Then you rinse and repeat. That's how it works.
Okay.
So it's
So,
not
so
it's
it's
not
not
circular.
it's not
You're
henpecking for evidence to support a theory that you can't you get away from. You think?
If it was, we wouldn't have Hubble tension, dude.
Well, it seems like the CMB. Um, I can't find a paper on it at the moment, but the original predictions was that it was going to be 50K, which kind of makes sense because the
It depends
early
on who you ask. Yeah,
early
like
densities.
Gamov, yeah.
That's right, the 50K, and then some other groups revised it down to 25K and um, less
Yeah,
than 5K, and then 2.7K, which is a little
okay.
bit problematic because if you wind the clock back, it makes that recombination period pretty cool.
No, it doesn't.
3012 is the number.
Yeah, that's not particularly cold. That and also
Oh,
that
well,
just intuitively makes
it's
sense,
about
really.
half the temperature of the surface of the sun, so it's not
Yeah,
a
and you'll
hot,
notice
dense
the
early
surface of the
universe,
sun, is a plasma.
and
So
it radiates light pretty well too.
yeah, but it's a plasma. The reason that we see the CMB is because it transitioned from being a plasma to being not a plasma.
And when it went from a plasma to not a plasma, then the light came out.
Well, it was already there. The light kept going in a straight line is what happened. It was there. It was just bouncing all over the place. It's sort of like a photon in the center of the sun takes a million years, 10,000 years, or something like that, 'cause- to get to the surface. But once it hits the surface, it just goes until it hits something else, like some alien eyeball. It's the same thing with the CMB. It was all bouncing around, and for a while the photons could only go maybe a few centimeters or something, and then they could go a few meters, and then maybe like a few kilometers. But the transition from non-cosmological scales to cosmological scales was pretty brief. It was quite short. And what we're seeing now is the photons that the last time they hit something, the last time that they scattered off something, that changed their wavelength at least, locally, was when the universe was about 380,000 years old. But at that point, the universe was very, very uniform. Not totally uniform, but like pretty darn uniform. It was uniform to like
Is
a
is
part
that
in
is that
10,000.
you're putting your hands apart? Does that include time and space in that space?
I don't. I'm not sure what you're asking.
Um,
I was mostly just gesticulating because that's
beyond
how I roll.
the this plasma thing, this recombination event or whatever you want to call it,
Mm,
the um, was there like was there space and time?
of course, yeah.
I mean,
I think I
outside of
personally
that plasma ball.
there was I personally don't think there was any outside of the plasma ball. I think the universe is and always has been infinite. Probably, it seems the most parsimonious sort of thing. So I think that if you could, and this might be a fundamentally ill-posed question, but if you could just instantaneously travel to any position along like a line of sight to where it is today, even though that's not necessarily super well defined, that you would never run to I don't think you'd ever hit an edge. I think that when they say the universe was the size of the period at the end of this sentence, which I think at that time the physical extent of reality was still infinite. But
In that space that you just mentioned, that you just described, and
okay,
I
yeah,
agree, that's the same for me. Was that entire space filled with what we have now in our universe?
it was filled with. I mean, it was not exactly the same. It was filled with matter and with dark matter. and radiation.
No,
It was
so
matter and
an
radiation.
infinite thing was filled with stuff that is our universe.
Sure. I,
All right. So how does that imply
I
it being smaller in the past?
well, the idea that when I say smaller, I mean all of the stuff that we observe today was all closer to each other in the past, and I don't think you disputed that, unless you do you
I
dispute
didn't.
that?
I would certainly dispute that.
Okay, I thought that you sort of
It's a
so
critical thing.
you don't think that galaxies at a sufficient distance are on average actually receding away from us. You
No,
think that the
no, not at
entirety
all.
of that effect is from
Gravitational shift.
okay. Do you think we don't know how to do math?
Um, I'm sure you do.
Well, I don't know how to do that math because I don't
Well, that
measure
math's fairly
gravitational redshift.
simple. I can
Yeah,
I could
yeah,
describe it to you with pen and paper, but would be much easier.
certainly. We
But
know how much gravitational
if you
redshift
look up something
goes.
like it was called back in the day, back in Hubble's day, de Sitter effect, and you might have heard people talking about light climbing out of a gravity
Yeah.
well, right? That's gravitational shift,
Yes.
and
And
what it achieves is a observer effect of distant objects getting redder. It's not the only effect, but the result is that
that's not
if the
true.
universe is completely uniform, you know, isotropic and homogeneous, um, there would be a straight there'd be a correlation between the shift of the light and the distance, which is a different distance redshift correlation.
Yes.
Right,
Yes.
that doesn't require an expanding universe, and the problem with expanding universe is
I,
that it's assumed that it's a Doppler shift, and it's not
it's
because
absolutely not. It's
yeah.
absolutely not assumed that it's all a Doppler
So
shift.
if it's not Doppler shift, and
It depends on what
and
you.
for some reason it can't be gravitational shift, what on what physics basis do you explain expansion redshift?
On the basis of expanding space. If you have a photon that is emitted with a particular wavelength, and then it travels through space, and space is expanding, then the photon will get stretched. That is redshift. Now,
But the light doesn't have a reference frame with space. Space is not a medium. That Aether theory was proven wrong.
this
Um,
doesn't require
so
ether theory.
so what you're describing is an adiabatic cycle process, isn't it?
What I'm describing is
Like
how
expanding the volume and reducing the energy, and it applies applying that to light. You're saying as the light goes through expanding space, it the photon expands, giving it a longer wavelength. It's a tired light theory, isn't it?
that's not a tired light theory now.
Or even say it's an adiabatic model.
I don't
It's
know if
you're
I would say
expanding the
that.
volume. Push bike pump. You get compressed air, and the nozzle gets hot. You compress the energy. Um, Over how a refrigerator works. You get compressed air and
Okay.
you release it to a lower pressure, and that gas gets cold. You're varying the volume of the space that energy is in. But
Those are they're not. They're
light
sort
goes
of
through
analogous,
space
but I
as
think
if
that's kind of
light
a
isn't
coincidence.
there.
I don't think that's. I think that analogy, while it sort of looks decent on its surface,
All
fundamentally
right,
the
all right.
two
How
are not
does
the
light
same.
couple energy into space?
But Well, so light is an excitation of the electromagnetic field, which is a quantum field, and photons are excitations above like the vacuum energy of that field. But now we're going into quantum field theory, which
Oh, I don't want to go anywhere near quantum theory. Everyone brings up quantum when they get in trouble. Um, that's true. It's just true. Um,
if
but
only quantum theory wasn't so good at predicting things.
but we can measure redshift, as you said. You were saying it, gravitational redshift.
Yeah,
And
and it's not all gravitational. Gravitational redshift occurs when light is climbing out of a um, gravitational potential, and that does not match what we see. We see versions of that. It's certainly a component. Light that was in an area of higher relative density by this very, very small amount when the CMB, when the universe became transparent, absolutely exhibits that. But it's a much smaller effect. The main one is just the expansion of space as it goes away. As distance gets larger is what I mean.
so space is a medium.
No, I I mean I I don't really know what you. It's it is where light exists. So if the light, there's nothing holding a photon like together. So like a molecule, a hydrogen molecule will not get bigger as space expands because it's being held by forces which dramatically overpower the expansion of space. A photon doesn't have that. A photon will just sort of get stretched along with space.
How
But
could a force like the strong or weak nuclear force um, not vary um, in 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 a different length of space?
I don't know where that came from. I don't.
Well, you just said
Well,
a proton or an electron won't expand in expanding space.
because there's a thing that's pulling it together. So space expands a little bit, and it just pulls it together more because like the Yukawa potential action, which is one um,
Well, together is
simplistic.
going to be further apart, isn't it? If space is what you're talking about as a parameter.
If it didn't have, so imagine that you had two spheres of metal just in a vacuum, nothing else going on at all, nothing
In space.
in space. Yeah,
Yeah.
just the entire universe is just two spheres of some material,
Yep.
and they are touching each other, and they are at rest at the beginning. Then space expands, so the center of those two balls moves apart.
No, no, no. The two balls get bigger and they stay touching together.
No, they, they but they don't get bigger because of the exact same reason why they're still touching. Like
What and what's that
so
reason?
locally, so saying they get bigger would imply that locally the distance between the particles is getting larger. But as it gets larger, then the forces are going to make it attract back together. There are forces that keep things at a certain equilibrium size, and unless you perturb that so powerfully in a very short amount of time, it's just going to always equilibrate to be that same size. It doesn't
If you got two
turn
balloons,
down the power
half
of
blown up,
the.
touching together, and you blow up both balloons by the same amount, balloons are just going to get bigger. They're still going to touch each other.
It's possible that my analogy was imperfect there.
Have you ever heard of the Big Rip?
Yes.
Right, well,
Well,
and that's one model of an expanding universe where
where that happened, where
where matter
eventually,
does expand, and it makes sense. A hydrogen atom is mostly space. You know that.
yeah.
You think a basketball being orbited by a golf ball 25 miles away. It's a hydrogen atom. Roughly speaking, on scales. And
Sure.
all the rest of space. If that space length changes, what changes? What in real terms changes? Except maybe the overall. I won't go into that yet.
Well, but okay, so they are attracted together. You have like a proton and an electron, and they are attracted and want to stay at a particular distance. If space expands, they move apart, right? But you didn't turn the force off.
No, they
You
don't move apart.
they they
No,
do.
they don't move apart. The
Well,
space in between them gets longer.
that's the same thing, bro.
No, it's not. There's no
Yes, it
relative
is.
motion in expanding space.
Okay. I'm defining moving apart as the amount of space between them, the distance between them becomes bigger. Those are synonyms to me.
No,
If they're not,
1 meter is still 1 meter before space expands and after space expands.
yeah, but
One meter doesn't become
if they
one
were
meter
one
doesn't
meter
become
apart,
1.2 meters, does it?
it does. Yes, it does. Yes, it does. Yes, it does. Yes, it does.
Ah,
This
no,
is
it doesn't.
Yes, it does. It literally does. That's literally what the expansion of space is. More space is like it's like being generated. It a meter, two objects which do not have any force attracting them or repelling them. They are at rest with respect to each other. The center between those two objects in an expanding universe expands. The distance between the center of those two objects gets larger over time. That is what expansion of space means. Even if neither object experiences a force, neither object experiences an acceleration, the space between them gets bigger. That's
Have
not
any physics to support that?
general relativity. It is a very natural consequence of the Einstein field equations that space can behave this way. It
Yeah, we know about space getting longer and shorter and time getting longer and shorter because we measure it, as you know, with gravitational shift and clocks on satellites and such. So we know space and time can get longer, and that's because of gravity, if you like. And you could imagine that matter actually makes space longer in that respect.
yeah, matter curves it, but
Well, it's justified in a curve in Einstein's field equations,
yeah,
with
but
Ricky tensor and all that kind of stuff.
Space itself is a dynamic physical object
What
in
is the property
relativity.
of space? What is the fundamental property of space?
What is the fundamental property of anything? I don't know what that means. I don't.
All right, you want to measure space. What do you measure?
What are we trying? What about space are we trying to measure? The energy
Well,
density of it?
that's the question. Is it like temperature, energy, or
Well,
you know,
what I'm
what
saying,
what 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 do you put inside your instrument to say what is space and time? We measure time. That's an aspect of space, and we measure those with clocks, right? And we can do a comparison between different
yeah,
clocks in different time frames, and we can a parameter of space is the length of time. That's one parameter, isn't it?
I'm not even sure what you're trying to get at. You said that we measure
We could
time with
measure perhaps
time with
gravity.
clocks.
Gravity is a property of space, isn't it?
The way in which space becomes curved due to distributions of mass, I suppose, would be a property of space, and it is one
All right.
that
You
is
plot it. You
explained.
plot a
That is
curve of space. You plot a curve of space. You got your graph paper out, and you're writing down numbers. What are the numbers that you're plotting to give you a curve?
I I don't know what you're asking me. I genuinely don't know what you're
All
asking
right.
me.
You're plotting temperature versus thermal radiation, right? You plotting the amount of thermal radiation of an object at a temperature. Right? You come up with a graph, right? You say space is curved. When you plot that out to get a curve, what are you plotting out? What are the
Oh, one
numbers?
thing you
What
could
are the
plot.
numbers on the X and Y scale?
Okay, one of the things that you could plot would be so on the X scale, it would be how large of a thing that you're measuring over. Okay, and on the Y scale, it would be what is the sum of the internal angles of a triangle, because that changes as space gets curved. So you can draw a triangle, and you can measure the angles inside of it, and if those angles are add up to less than 180 degrees, then you're in a space with negative curvature, and if they're in a thing that add up to more than 180 degrees, then you're in space in a place with positive curvature. As one example.
So, okay. So, isn't it once again that a little bit circular? You're
No.
measuring the shape of space by assuming space has a shape.
Well, I mean, if you have that's that's I don't know how to like even interpret that. It's like saying you're calculating the sum of two numbers by assuming that numbers have sums. Like I I I think we've started to very much speak past each other. I think what you're trying to say is that there's no there. It's all just a self-consistent story that physicists are saying.
We've gone in a little bit into relativity, but so we can go away from that if you like. Um, we have a visible universe. Do you agree with that? We have the visible universe, and beyond the visible universe,
Oh,
there
I'm
is
sorry.
a
Okay, yeah,
universe um, beyond our observation.
yeah, sure.
Why isn't the source of the CMB um, from why? How is that not from beyond our visible universe?
Well, it's from just barely, kind of inside. How's it not from beyond our? Well, if it was beyond our visible universe, it wouldn't be visible.
Well,
So
yeah, that's a good point.
it's a tautological point. I don't think I actually won
Well,
anything there.
if you look at people's like people talking about the Hubble Deep Field, and they were saying if you pick the most distant object that you can see, something that's 13.75 billion light years away, um, beyond that is the source of the CMB at some point, at some distance.
So the CMB, the surface of last scattering, is when you look at a CMB photon, there was a most recent thing that it scattered off of, and that was when the universe was about 380,000 years old. I understand that you disagree with this. I'm you know giving the model. That surface was just inside the observable universe from our perspective. It's the CMB is kind of the edge of it's not quite there. There is a difference, and there's a bunch of expansion and stuff.
No,
But
I
the
fully
CMB
get
is
that.
not.
Yeah.
It wasn't beyond anything. That that's just not a thing.
So if we looked at the Hubble Deep Field and we had our magic teleportation instant travel device, and we instantly teleported to that most distant object,
Yeah.
um, would we be any closer to the source of the CMB?
Nope.
No. Right. We get the CMB into our eyes, into our antennas and instruments, as a continuous signal delayed by some distance, and the speed of light. So whether it's 13 billion years or 50 billion years, some distance away, and it's continuous. So where can we instantly teleport to to be at the source of the radiation, the CMB radiation? Where can I instantly teleport to be at the transmitter site?
This is a point you've raised multiple times, and I think it reveals a fundamental misunderstanding of what the CMB is. And you've even mentioned in our discussions an analogy that I think explains the point perfectly well, and I think it's worth talking about because I don't see which part of it you're sort of missing. So the analogy that I'm referring to is the infinite field of drummers.
That's
Okay?
that's the
So, yes. So imagine an infinite plane, just like a two-dimensional, like that room in the Matrix, where it's all white and everything. It's just infinite in all directions, and it's filled with drummers. And those drummers hit their drum once. Are you ever going to stop hearing the noise?
um, uh, if I hear the noise continuously, I can instantly teleport to somewhere where a drummer is drumming.
Nope, no. They
Why
hit
not?
it once. Because they hit it once, and when you instantly teleport, you've teleported after they've hit it.
So
And,
if I know
yep.
a drummer is going to drum and it's going to take a week for it to be here, I can instantly teleport one light week away and be at the source of the drummer.
Yes, but that's not the situation that we have. What you're doing there is you're saying, okay, I know that the sound I'm hearing, I'm going to hear it at this time, and I also know that that particular fluctuation of sound waves was caused by this drummer at this distance away.
Doesn't
That's
that
not what's
model require that
No.
your universe is infinite instantly?
No, it does. I'm asking you again. I want you to think very carefully about the answer to this question, and then we can go into it. But if an infinite field of drummers all hit their drum once, when do you stop hearing the noise? And does it matter where you are?
So the CMB image is not an image of our early visible universe,
That was
because the
not that did
drummers have
not
already long gone.
yeah, that didn't sound like an answer to my question. This analogy I think is a great one, and it's why I'm
All right,
pressing for a
all right.
question.
I'll take your analogy. If the universe was populated by me's, would any of me's be at the source of the drama? If I was infinitely distributed across the universe.
The source doesn't exist anymore. The sound waves exist, okay? The source doesn't presently exist. A source that is infinitely spread apart in distance. If it releases sound at one moment, that sound will be present in the universe forever. So I want to ask you the question again. In an infinite field of drummers that hit their thing once, do you ever stop hearing the noise?
Yes.
When?
When the inverse square law takes hold.
That. Okay, so that makes it that actually doesn't work like you think it does, because guess
Doesn't it?
what? No, it doesn't. It doesn't.
Oh,
Because
why is that? Every
because
drummer's drumming.
are you gonna let me finish?
Every drummer's drumming directly at me, are they?
They're all drumming directly at you and every other point in space. What? Okay, how many of them are contributing to you? How many drummers are you hearing as it goes out? You're hearing a number of drummers that increases as the square of the distance, because that's how spheres work. And the intensity of those drummers of each individual drummer is getting weaker as the inverse square of the distance. Those cancel each other out. You're going to hear the same tone for all time. It's going to be a constant, even hum. Forever. Everywhere. The inverse square does not make it weaker. It makes the contribution from one individual drummer weaker, but the number of drummers that are hitting you, even in an infinitesimal, like little patch of the sky, is also growing as the square. Square, inverse square, cancel each other out. You hear a constant signal that never gets any weaker, and the only reason it would change in pitch, other than like dispersion, the only reason it would change in pitch would be if, for example, the space were expanding. Or I'm assuming also that the field of drummers was at rest.
Strong signal. It's a strong signal, but it's not gargantuan signal.
No, because you're right. The analogy there would be something like, if they hit the drum softly versus hard, what is the density of the drummers? Those would be things.
Well, we're talking about wavelengths of photon wavelength. So it's not soft or hard drummers.
Well, the amplitude of the signal. Amplitude of the signal. Oh, okay. Then we're not talking about the amplitude of the CMB signal. We're talking about the. So when you said amplitude,
well, photons don't have an amplitude. A photon doesn't have an amplitude.
The number of photons that we detect per second.
That's an intensity. Yeah, that's an intensity. That's not amplitude.
Okay.
Coherent light, like a radio signal, has an amplitude. I agree with that. Where all the waves are in phase and coincide,
they don't have to be in phase.
Overall larger signal.
You can have an RMS deviation of a thing. Okay, I don't need. We both understand this part of it, I think. Okay, but well, apparently not, because it. So
well, a soft drummer and a hard drummer. So the drummers are getting softer. When? I mean, if as you're saying, if I understand what you're saying, that if the drummers are an expanding field at the speed of light, all drumming,
they're not expanding at the speed of light. They can be expanding at or contracting at whatever.
I mean, receding at the speed of light. The length of time.
The location of the drummers that are responsible for the fluctuation that you are hearing at a given point of time, that location is receding at the speed of light.
Yes,
Even if the
that's
drummers
what
can
I
all
said.
be
Yeah,
stationary.
yeah.
The drummers can all be stationary. Okay,
So
but
the CMB from you is a slice of the universe as we see it receding away from us at the speed of light.
yes, it's a little more. Yes, because it's also there actually is expansion happening.
Yeah,
The
yeah,
field
yeah,
of drum,
yeah. Yeah, right.
but
If you include expansion, it's not going to be 13.4 billion years. It's going to be 26 or some other figure because the light has gone through space that's expanding
yeah, yeah,
from your model.
but
Yeah,
yeah, yeah, exactly, exactly. The CMB
yeah,
is a snapshot from when, in that case, it wasn't drummers drumming. It was, it it was the photons suddenly stop being scattered and just going straight.
yep, yep. So
So
one
yeah,
aspect of the CMB that's used to establish its, origin as from the Big Bang is that the temperature variations in the CMB correspond to um, matter that we see in the visible universe. Do you
uh,
accept that?
partially, it does. Um, it corresponds to the mass distribution that we see
Yeah,
in the
yeah,
visible universe.
yeah. Due to the
But
variations in density of that recombination event.
well, dude, yeah, I think that's essentially correct. Yeah.
Sorry. So if you think about it that way, what we're seeing, let's say we look at a distant galaxy and we see a increase in density of the CMB along that axis. So we see a distant galaxy, and we say that um, that galaxy, that region of space, has that galaxy in it because of the variation density of the CMB that we attribute to it from the CMB. Um, doesn't that mean that we are seeing the light from the galaxy, um, and also light from the density um, variation that is attributed to that galaxy being there. So we're seeing the light from the same matter twice, at two times. We're seeing the matter as it was when it was radiating the CMB, and we're seeing the matter as it is as a galaxy. So if
There's
we had those variations that didn't correspond with our galaxies and the matter that we see in our visible universe, but had the same, had a like a recognizable distribution, that would be better evidence that the CMBs um, from the Big Bang, wouldn't it?
so you're talking. So the length scales at which we see objects like that have to be over like 100 megaparsecs. The universe doesn't really look uniform until you get to length scales larger than about 100 megaparsecs. And 100 megaparsecs is a really, 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 really big distance. And so if you're talking about we see a galaxy cluster and we see just directly the light from that, just glowing stars and stuff like that, right? And that's we see it once. That's what you're saying. And then also what you're saying is that the CMB from that region of the sky has been modified because of the mass distribution there, and that's why we're seeing it twice. Is that how would I do it at summarizing what you were saying?
Yeah, I think that's it. Yes.
Yeah. What I'm saying is that those two effects, when you're talking about clusters of mass that are 500 megaparsecs large, those two the CMB is from way, 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 way behind the galaxy, but way, 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 way behind the galaxy is a fraction of that overall distance. So when we say that it sort of looks like they're from the same thing, they're not. They're from a big old like sort of cluster of things which form a structure that is larger or on the scale of hundreds of megaparsecs.
So
So it's not the same way.
we would
It's like
expect to find then galaxies in a line following um, a higher density CMB
it would be sort
recombination.
of that when recombination. I'm pretty sure that it would be. God, I'm so terrified that somebody like an actual cosmologist or astrophysicist is gonna watch this and be like, "Oh, Vandy, like why did you leave your lane?" And
Well,
like, I'm sorry.
just, just, um, you know, common sense analysis.
Oh, bro, I common sense analysis has shown me that common sense analysis is a stupid thing to rely on. So, and besides, I spent all those years in school to get better than a common sense understanding of physics.
That's
So,
right. You learned how to analyze and interpret data
yeah, and do yeah,
and
among
be
other things.
critical and
Yeah, critical
um,
thinking and problem solving. Yeah, that's
yeah,
how.
and not to draw a conclusion and make a claim that it can only be this way because
And
I can't think of any other way or that no other
I want
way
to be
is
clear.
possible.
I want to be clear. I have not made that claim. If you think I've made that claim, then I want to emphatically state I haven't. What my
Well,
claim is
you
that
said
this
you
is the
could think
best
of no
option
other way. You could
because
think
I
of no other
can. That
way
doesn't mean
that
that there
the
is no other way.
CMB could be just black body radiator.
Because well, it is from a black body radiator. It's just from a black body radiator that was a uniform distribution all over because that matches the data better. The reason I believe that is because it's the best explanation I am aware of. It would be silly for me to not apportion my belief to the evidence. If a better theory comes along, I will change my mind. Physicists change their minds, okay? Physicists change their mind about neutrino oscillations. Physicists change their mind about dark energy. Physicists change their mind about whether the universe was expanding or contracting. They change their mind about all sorts of things.
So if you didn't know about the Big Bang, you did your physics degree on another planet,
Mm-hmm.
and you
Yep.
know all about physics and the laws of physics,
Yep.
and you have a couple of radio engineers come up and tell you that they see a slight increase in the noise floor that they weren't expecting at a certain frequency in the microwave spectrum. It's still Gaussian noise, even distribution, but um, it's a little bit higher than what the expected background noise was. Um, and you also know that the sun and the solar system are in the remnants of a supernova, and we live in a dust cloud that goes out 8 or 10 light years away, that's full of dust, that's um, at a thermal equilibrium um, um, at 2.7 Kelvin.
You're starting to
Um,
add premises that I don't agree with.
what? What premise?
The premises that we have a uniform constant density sort of halo of dust at 2.7 Kelvin. That simply doesn't match observations. But you're
It's a fact.
uh, we spent time on this. It's due to your misunderstanding about how materials radiate based on their emissivity
Do you
properties.
think there's no dust in our space?
Of course, there's dust. We understand the dust pretty well. The Planck satellite was one of the main groups of scientists that put the nail in the coffin of the bicep 2 result, because the bicep 2 people didn't take the contributions of dust to the polarization spectrum of the CMB into account properly, because the polarization details of the CMB are a lot more subtle and a lot weaker depending on properties, and so it becomes a lot harder to decouple things like dust. But we do understand. We understand and we measure and we model foreground contributions to noise, and we can use that to subtract it out. And we do that based on other avenues of physics, like how we know that that matter generally interacts with radiation. We can learn an enormous amount about how matter interacts with radiation in laboratories. We don't need to rely solely on astronomical observations. We can use our in lab local physics of somebody who never leaves the basement in order to model sources of noise, such as, for example, dust.
All right, yeah, you bring up bicep, which is a good argument, and you know what the result ended up being for bicep.
Yeah, they had to retract it. It was really embarrassing.
Yeah,
They didn't look at the dust properly.
And the other thing is, they didn't find what they were looking for, or they thought they found it to 6 sigma or whatever, very high confidence, and they didn't find anything, and subsequent biceps. And see, the problem is, that was a really big deal because there is no clear, unambiguous signature
Of inflation.
that
Bicep is about inflation.
that differentiates what is local dust and what is Big Bang radiation. And now the signature, the key signature that you hang your hat on, is that it's a black body radiator.
Yeah, because that is a much less ambiguous signal, and also you can't use an example of physicists showing how this team of physicists failed to differentiate it by themselves doing the differentiation to make the point that it's impossible to differentiate the signals.
They didn't observe the effect. Let's just get it right. They didn't observe what they were looking for. They thought they did.
I know they thought they did. They were wrong. Physicists are not gods. They were wrong. There's plenty of things that we look for that we don't find. And it's just because you don't find it doesn't mean it's not there. It means that it wasn't strong enough for you to detect it in the way you were detecting it. It means it might be weaker than you thought. It means that your instrument might not have been designed properly.
Yeah.
It means that your analysis might not have been designed properly.
And that is the history of Big Bang cosmology, isn't it?
It's the history of all of physics, of
No,
all
it's
of
not.
science.
No, it's
It
not.
absolutely, it totally is. Also, the black body spectrum is a completely different physical effect from B-mode polarization. It's a completely different
I fully agree.
effect.
I know the physics behind it. The idea was that the light from this Big Bang has travelled a long way through space, and it undergoes passage through magnetic fields and undergoes Faraday rotation. So you get a polarization pattern imprinted in the CMB. Bicep 2 was looking for that. Bicep 2 analysed the data
That's false.
and found it.
You're incorrect. That they were not looking for polarization modes in the CMB. Full stop. They were looking for polarization modes that were specifically deviated from a non-inflationary model with an inflationary
pattern.
model.
They were looking for a pattern in the CMB.
And they haven't ruled it out. They got a null result, not a negative result. Those are not the same thing. That's like saying that somebody who tried to measure the speed of light, but because their measuring apparatus only is valid up to 200 million meters per second, and therefore they measured something consistent with zero, that they proved the speed of light must be infinite.
Oh, yeah,
It doesn't
okay.
follow.
Well, all right then. Using that mindset, what would falsify the Big Bang?
An alternative model that explains the data better, and you don't have one. You think you have one, you simply don't.
The
The
data
system
that
you're
you predicted.
describing, the system that you're describing would not look like that. The dust would get hot, it would be clumpy, it would not look uniform, it would not be at a temperature of 2.7 Kelvin.
Why not?
Because it
Why
because it
why
would
would
be,
it act any different than any other matter? Than your cup of
what other
coffee on your
matter is
desk?
at 2.7 Kelvin?
What?
The matter in the universe is
All matter
no.
is at 2.7 Kelvin,
Are you at
unless
2.7
it's
Kelvin?
yes, and
What the
a
fuck?
lot of other higher temperatures.
That's not how temperature works. That's not how temperature works. No, you are not at 2.7 Kelvin. I don't know how you can say that with a straight face. That's an absurd statement. It's absolute madness.
Have
It
a look at
indicates that you.
have a look at the black body spectrum chart. You see it's a
What you're
spectrum.
saying?
You see it's a spectrum. You see it's a
Yeah,
spectrum. I radiate thermal energy at 2.7 K.
you radiate
I radiate
energy.
thermal energy at 2.7 K.
No, you don't.
And I radiate thermal
That
energy at a
statement
lot
means
of other
something,
temperatures as well.
which means that you're not radiating at 2.7 K.
Yes, I
Radiating
am.
at 2.7. No,
Look at the
hold on.
spectrum.
I okay. I think that I don't. 2.7 means that if you plot the number of photons as a function of wavelength, it follows this pattern. If you're also radiating at other stuff, then it's not 2.7.
You
That
saying
that's
that you're not radiating any thermal energy at 2.7 K?
I'm
Are
saying
you?
that yes,
Yes, thank you.
because that doesn't mean what you think it means. It doesn't. I am radiating energy. I am radiating it at all wavelengths, all, except for probably really, 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 really high
Well,
ones where you start to get matter-antimatter conversion.
statistically, you probably are.
I am not radiating with a 2.7 Kelvin spectrum. Okay,
You're
I
not
am
radiating very
radiating.
many X-rays.
I am radiating. I am radiating way, way, way more infrared energy than an object at 2.7 Kelvin. Therefore, I am not radiating at a 2.7 Kelvin blackbody spectrum. This, I don't.
That spectrum, that's the point, isn't it?
I know it's the point. How do you not know it's the point?
So,
The spectrum. This isn't. I don't understand what you're not getting about this.
oh yeah,
Because
Andy's gone off. You just admitted that you radiate 2.7 Kelvin.
no, oh,
So what's your
Jesus
problem?
fucking Christ! No, I didn't. What?
Yes,
Okay,
you did.
so
You said yes.
I said I radiate at all wavelengths, and then you asked, "Do you radiate at 2.7 Kelvin?" And I said no, and you said, "Thank you for saying no."
Oh,
So-
I thought that was a yes. Sorry.
You thought no was a yes.
Yeah,
That
I thought
explains a
you
lot.
said yes.
Well, I didn't. Maybe you should listen.
All right. Can I ask you again? Do you radiate at 2.7 Kelvin?
No, I do not. Radiation at 2.7 Kelvin looks like this. I radiate like that. What your point is that I am also radiating at these things. My point is that the
You are.
statement, and that is true. My point is that the statement radiating at 2.7 Kelvin means it looks like this one and not like this one. And that I am radiating at all of these frequencies. So is everything else, except for perfectly transparent objects, which don't exist. but I am not radiating at 2.7 Kelvin. If it doesn't look like this, it's... Sorry, if it doesn't look like this, it's not at 2.7 Kelvin. That's like saying that... It's like saying that if you listen to the noise from an aircraft jet, that you are hearing Beethoven's symphony, because inside all of that
If I got a
crazy
very
noise...
precise bandpass filter and
Yes,
set,
and
the,
it
and
goes like
set the
this.
wavelength of that bandpass filter to 2.7 Kelvin, and I pointed at you,
That
would I
doesn't
see a
make...
signal?
Not a blackbody one. Unless you're talking about something that literally
Would I
produces
see
exactly...
thermal radiation at 2.7 K?
No. Categorically
If
no.
I-
You
if
will not
I-
see thermal radiation. It will not be a thermal distribution of radiation. That what you just said has a specific
What's
meaning.
thermal
and
radiation
it's
to you?
this. It's radiation that has a spectrum of a black body.
It's the wavelength of the light, isn't it?
Yeah. What?
That's what thermal radiation is.
The wavelength of the light?
Yeah.
Thermal radiation in this context, I am interpreting thermal radiation as being the radiation due to due to thermal emission. It doesn't necessarily have to be at exactly black body. You can have emissivity.
But what is it?
corrected.
It's light, though, isn't it?
Yeah.
Yeah.
Darryl, are you having fun?
Oh, yeah. I think we've gone a little bit off the...
Yeah,
We
just
absolutely
slightly.
haven't.
Just
this
what?
is not
Are you
off
sure?
topic.
Are you sure?
100%. I'm 100%. He's saying that because I'm also radiating here, that this can be described as this. I don't know what else to do other than to say that no. Saying you're radiating at a black body spectrum of 2.7 Kelvin means that the spectrum looks like this. My spectrum, your spectrum, everybody else's spectrum doesn't look like this.
Well, you
Because if it did,
if
you'd
it
be
was
dead,
exactly
'cause you'd be frozen.
2.7 K, there's no spectrum. It's just a wavelength.
No, whoa!
It's just a wavelength.
What?
Yeah.
You think that a perfect black body of a fixed, well-defined temperature, you think it emits at one wavelength?
No, I didn't say that. I said one wavelength.
That's why I'm asking you.
One
because it
wavelength
sounded like you said
corresponds to one temperature, and
It-
a range of temperature. Like, all right,
that.
I know
No,
what
the
I know
shape
what you're
is a
saying.
spectrum.
You're saying if you're 20 degrees C, you're radiating thermal energy at 20 degrees C.
I'm saying no, I'm saying something more precise. I'm saying that I'm radiating with a spectrum that has a relative intensity.
So what is the spectrum you're talking about?
This
It's
is
a-
the
it's-
black body spectrum.
It's the wavelength of the light, isn't it? Which is corresponding to a temperature. So even
my
if you're
God.
at 20 degrees C, you're also radiating thermal energy at 19 degrees C because it's a spectrum.
Yes. Okay, that's
Right.
like
So
saying
if you're
that this is
if
this
you're
a
at
circle?
if you are at or above 2.7 K, then you are radiating at 2.7 K.
Radiating at 2.7 K means that the peak wavelength is there. My peak wavelength is not there, therefore I am not radiating at 2.7 K. It's a distribution, and I'm really shocked that you don't follow that, because it's just not that hard.
Well,
You know,
well,
well,
looks like a
okay,
pattern.
guys, we are coming close to time. And this doesn't have to be the last conversation ever. I mean, if Daryl's open to more. We do have some questions from the chat, and then we can talk about perhaps like scheduling another conversation next week, next month. Yeah, whatever makes the most sense for, people on a Saturday. Daryl, what do you think?
Sure.
Doc?
Yeah.
All
Although I
right.
think we covered a fair bit today.
Yeah, we've covered
Something.
so much today. And I think like the particular topic we're in is just kind of like the horse is dead and we're still beating it. So maybe it's a good time to kind of regroup, take a deep breath, maybe a week off or a month, whatever. We have a group chat. We'll work it out, whatever works best for us. And the chat seems pretty happy. So um no, I really enjoyed myself tonight. Daryl, you good?
Well, that was the main thing. I'm not trying to. I was really reluctant to have a kind of um, flat Earth level debate
No, I don't
where
think
we
this.
Hopefully you
people
don't feel like
start
that
talking
happened.
past each other and
Yeah, no.
well, we've
Oh,
got a little
okay. I
bit
see
like
what you're
that.
saying.
We've got a
Because I
little bit
think
like
you're
that towards the end, maybe.
Maybe. Okay, maybe. Sorry. I get really excited because yeah.
you're passionate. This is your well, kind of your field. This is akin
Yeah.
to your. It's in the physics realm for sure, and I know how much you love physics. It's kind of like how I get when Mark Reed starts pissing on psychology. Um, all that aside, Um, Dara, I think you've been a great sport. You've been, I think you've been very knowledgeable. Like a lot of people in the chat are saying that they're having a hard time following the conversation, and you've been, keeping up. You've been giving as good as you've been getting. So I think you've come across really well.
Makes them good.
Do you have a couple of minutes to take a couple of questions that came in from the chat?
Yep, certainly.
All right. So Germania, who I don't believe is still here, wants to know from both of you if you know how magnets work.
BFM.
Maxwell's equations. There we go. Go.
All right, from Sydney Raptor. Question, I believe for both of. Wait, oh no, question for Daryl. Have you looked up methods of differentiating between redshift factors, Doppler, cosmological, and gravitational?
That's almost impossible problem, and that's what I think cosmologists um, would struggle with. Even Hubble struggled with it. If you look at his plot for the redshift,
Hmm.
I asked Eddie about whether he could find that the original
Oh.
Hubble paper, but the data set is all over the place, and you've got a lot of things that um, make it uh, hard to determine what is what because um, the relative mass of the galaxy is going to cause gravitational redshift if it's more massive than us. Um, Doppler shift from relative motion, um, and um, redshift from gravitational shift due to greater distance.
Doc, did you want to respond?
Yeah, I was gonna say I found so in the book that I got in preparation for this. This is a reprint basically of Hubble's original data, and Daryl's point is that there's a bunch of scatter and stuff, and below is a more modern and recent measurement of the same stars, but with like error bars and stuff, and also I think that the distance scales are different because they like learned a lot from one to another.
The
But
original Hubble expansion put the universe at younger than the Earth. It put it
yeah,
at the universe
I think
about 4 billion years
that's
old.
probably I think that's true. Yeah, I
Yeah,
think that but the thing about Hubble
so
was
that's a
not.
problem.
I mean, he didn't know enough to. He didn't have an accurate enough calibration
Yeah,
ladder.
yeah.
What he had was relative things. Hit Hubble's observation was that that line has a slope. Do you deny the line has a slope? No, you don't. So you don't actually have a problem with the Hubble
No, well,
observations,
that
in my
line
opinion.
is going to have a slope because of gravitational shift.
Yeah, that no, it wouldn't. But
Yeah,
okay.
well, we can go through that another time, but it will.
Yeah, sure.
That's how gravitational shift works.
I am familiar with how gravitation. We'll go
Well,
over it another time.
if we can get some way of doing, presenting some pictures and diagrams, we can work through that, and I can show you how you can get a redshift with distance relationship from gravitational shift.
Okay,
Wonderful.
question from Titan Uranus. Dr. Tapioca Weasel, if you programmed a Star Trek holodeck human from the DNA up and fed it from the replicator instead of the holodeck generated food, would it metabolize it? I don't know what I just read.
Can you read it again?
If you programmed a Star Trek holodeck human from the DNA and fed it from the replicator instead of the holodeck generated food, would metabolize it?
I
Can't
actually
speak to
don't know
that.
the answer to that. The in universe exam. I mean, obviously, the answer to that is that the holodeck is fictional, um, and so
Yeah,
are
I caught on to
replicators.
that.
But
If you teleport,
but
are you still you?
yeah,
It's a great
also a good
question.
question. Also a good question. I don't know actually. That's an interesting. The answer I think is probably no, and I feel like that might have been the subject of some episode where like a holodeck thing. Like I could imagine an episode of Star Trek that maybe I've seen and I've just forgotten it, where there was like a civilization that evolved in the holodeck world, and then like the physical world came in and they started getting sick because they couldn't metabolize the food properly because it wasn't hollow food. Like I can totally imagine that being a uh, plot like of a Star Trek episode.
Yeah, somebody pissed off Santa.
Okay. Yeah, my bad. Sorry, Dad.
And Purple says, feed it into the teleporter as a pattern for it to reconstruct.
Yep.
All right. From Ember, why couldn't the CMB be a black body at 2.77 Kelvin rather than a red-shifted signal originally at a higher temp?
What, why does it have?
Hey,
What?
hey.
Why does it have to be that? Because it isn't. It is redshifted from a higher temp. It when 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 it was created, the
That's a good
temperature of
question.
it was about 3,000 Kelvin. The reason it couldn't be at a lower temperature is because there isn't a source of blackbody radiation that is at that temperature that has those spatial and temporal properties because we checked and we looked and there isn't one. It's we don't see that. What we see is something that comes from way, way, way farther away. We see something that correlates with objects and structures at distances that are not remotely local.
Okay.
But it is actually it is not a priori obvious, but it is mathematically true that a red-shifted black body is still a black body. That's not obvious, but it is true.
Daryl, anything to add?
It was a good question. I
Indeed.
think the problem is that um, I'm looking for something that's going to smack me in the face as, yeah, dude, this can't come from anywhere else. And um, essentially, picking two data points on a Gaussian noise distribution um, noise floor doesn't make me have a beyond reasonable doubt um, idea that it came from something like a Big Bang. That it's a black body perfectly doesn't cut it for me.
Okay. Well, maybe we can tackle that a little bit more in depth on, if we speak again. From Daniel Gable, I think the type 1 supernova data suggests we're in a new accelerating expansion phase, or there was a question. Does the type 1 supernova data suggest we're in a new accelerating expansion phase?
The Type 1A supernova data suggests that the rate of expansion is currently accelerating. In that sense, yes. So the rate of expansion um, has changed over the age of the universe, and it now the expansion is accelerating because the universe is not it is less gravitationally bound than it was before. Because yeah, so yeah,
Comment from Darryl Frost in the chat. He didn't learn a thing. And earlier, there were quite a few comments in the chat just expressed in their displeasure at talking about perfect black bodies and mine not being brought into the equation.
ooh, that's a good point.
Yeah. So shame on both of you.
That was just assumed.
Fair enough. See, listen to the smooth talker. It's
There's certain axioms in nature.
all right. Gentlemen, I had a fun time. Thank you so much for your time tonight. I know that you have, I don't know, it's a Saturday, you have loved ones. But thank you for spending some time over here with us and helping many of us learn something about, our
Maybe
reality.
maybe next time we can explore what a no Big Bang universe would look like.
That actually did come up too. And I know that when I originally talked to you, you didn't want to bring that up. But we
Oh,
would
well,
love
yeah.
we would love to hear. We would love for you to speak on that. But again, just a conversation, not a debate, not a inquisition. Just if not the Big Bang, then what
I mean,
would there be?
I think it's pretty clear to all people in the audience that if anybody's gonna like lose it, it's clearly me. Like clearly, I'm the one who gets all hot and bothered.
It's your field. I feel you. I do. Um, I really do. But and like I'm, you know, not even clinical, so there's that. But yeah, I would like to say again, thanks to all who attended. Make sure you do click the like button on your way out. And I know I'll put this in the chat. Um, Nitty is going to be starting in about 2 minutes. So since for whatever reason YouTube won't let you raid unless you have 1,000 followers, we're going to have to do it the old-fashioned way.
Woo.
All right. All right. So, but I do want to see everybody here back tomorrow around this time for Bad Science Sunday. We'll be on with Ryan. All right. All right, guys. Say bye to everybody.
Bye.
I